Okay, so we talk about generalized version of the ElGamal cryptosystem. We have seen the ElGamal cryptosystem over ZP, but this can be over any group G. So, so not only we restrict ourselves on ZP, so we will talk about generalized version of the ElGamal cryptosystem. So, for that we need to discuss the discrete log problem also in that group. So, suppose we have a group G and we have a operation star in that group. So, this is a abelian group. Okay. Now, we define the discrete log problem over this group. On this group, this is the generalized version of the discrete log problem. So, the problem is we have given G alpha beta, where G is a finite group and this is the operator on this group, and this alpha beta such that we have given that alpha belongs to G and beta belongs to H, where H is basically is the group subgroup generated by this alpha. So, this is alpha to the power I and I is greater than or equal to 0. So, it is basically a subgroup generated by alpha. So, alpha that means alpha, this is alpha square means alpha times alpha. So, alpha cube is basically alpha times alpha like this. So, alpha to the power I is basically alpha, we are operating alpha I times like this. So, this is the group subgroup generated by this alpha. So, this is a cyclic group, this H is a subgroup of G and this subgroup is a cyclic group. Okay. So, now we define the this beta. So, beta is basically we choose a and we calculate alpha to the power a. So, that means alpha a times. So, this is we say beta, this is the beta. So, we have given G group, we have given the generator and we have given beta, and it is hard to find, the question is to find alpha, question is to find a. So, that is the discrete log problem. So, if it is hard, then we can think of a have a ElGamal cryptosystem based on this. Okay. So, for the simplicity we are taking so this is the problem of this is discrete log problem. So, for the simplicity we are taking our group to be a cyclic group. So, this is the general case, but suppose we have a group cyclic group, suppose G is a cyclic group and say alpha is the generator of this group, alpha is a primitive element. So, it can work on the subgroup also. If you take any alpha, then it will generate a subgroup generated by alpha, that is H, but for the simplicity we are taking G as a our whole the group is a cyclic group and alpha is a generator, and we choose a which is between 0 a less than equal to the size of the group minus 2, and we compute beta. Beta is equal to basically alpha to the power a, which is basically alpha cross alpha times A times alpha. So, now the discrete log problem is basically given this group along with this generator and the beta, which is basically alpha to the power A. The finding A is hard. Finding A is hard. So, this is the finding A is the called discrete log problem, and this is, if this is hard in this group, then we can have a ElGamal cryptosystem based on this group. So, how? Then let us talk about that generalized ElGamal cryptosystem based on this group. Okay, so Alice and Bob Alice wants to send a message to Bob. So, Bob has to get Bob's public key and private key pair. So, this is the setup phase Bob has to run. So, Bob choose a group, that generalized group along with this operation, and alpha is a primitive element, is the generator if this is cyclic group. So, we take a cyclic group is the generator of this group, and then Bob choose A, which is basically secret to the Bob. This is the private key, and then Bob compute beta, which is basically alpha to the power A, which is alpha times A times alpha. Okay. Now, so this is A times alpha, and now Bob publish this. So, this is also this beta is public, and in this group the discrete log problem should be hard. So, now what is the plain text space? So, plain text space is basically G, and the ciphertext is basically G cross G, and the key space is basically, this is the key space. So, key has this component G alpha A beta such that beta is equal to alpha to the power A. Okay. And only this is private or secret key, and remaining these 3 is public key of Bob, public key. So, Bob made this public. So, this is EB. EB is basically the group G, alpha and beta. Okay. So, now Alice wants to send a message to Bob. So, what Alice will do? This is the ElGamal cryptosystem. So, Alice will choose a secret. So, this is the encryption, and as we remember in ElGamal, encryption has a G cross G. So, y1 and y2 has 2 part. So, before that Alice has to choose a random number k. Alice choose a k, and then what Alice is doing? Alice is encrypting using this using the Bob. So, this is the encryption using the Bob public key on the message. So, message is coming from along with this random number k, and this is y1 y2 basically, and sending this y1 y2. So, what is y1? Y1 is basically alpha to the power k, and y2 is basically x masking beta to the power k. So, alpha to the power k means alpha time k, and so this k is coming from 0 less than k less than g minus 2. So, this is the random number Alice is choosing. Then alpha times this this group operation a times k times on this alpha. This is basically alpha k times. Okay. So, this is alpha to the power k, then this is k times beta, then followed by this x masking and send it to Bob. Now, how Bob will decrypt it? So, this is the encryption process, and for decryption, so upon receiving the ciphertext y1 y2, so this is the decryption made by Bob. So, upon receiving this ciphertext y1 y2, what Bob will do? Bob will just compute y2 into means this operation y1 to the power. So, Bob is having secret a, y1 to the power a inverse, and this should give us basically x. So, this is the decryption for generalized ElGamal Cryptosystem. So, if we have a group, if we can get a group G which is having a generator, and so if we can get a cyclic group G which is having a generator, then we can think of an ElGamal Cryptosystem. So, this is the generalized version of ElGamal Cryptosystem. So, based on this idea, we can have what is called ElGamal Cryptosystem over elliptic curve points. So, let us talk about that, but the idea is this. So, if we can have a group from anywhere, I mean maybe from elliptic curve points. So, that ZP, we know ZP was a group ZP star. So, for that we have a elliptic curve version, for that we have a ElGamal version. So, now we know the elliptic curve points over ZP. So, now we talk about ElGamal Cryptosystem. Over elliptic curve points. Okay. So, we have seen, suppose we take this elliptic curve for example over ZP. So, this is say xy, and xy is coming from ZP cross ZP, ZP cross ZP, such that where p is a prime, y square is congruent to x cube plus x plus b mod p, and AB are coming from ZP, and we have this non-singularity condition 27 b square is not congruent to 0 mod p. Then we know this along with this theta, this form a, this is the elliptic curve points, and this will form a groove, abelian groove under the addition operation, and this addition operation is defined as like this. So, if you take any two points p q from this, if you take any two point p q, so say p is equal to x 1 y 1, q is equal to x 2 y 2, and if we know that if q is equal to minus p, this is the point at infinity. Now, if q is not equal to minus p, then p plus q is basically r, which is x 3 y 3, and we know the formula for this. So, basically x 3 is so x 3 is basically, so x 3 is basically lambda square minus x 1 minus x 2 mod p, and y 3 is basically lambda into x 1 minus x 3 minus y 1. Okay. And the lambda is, so this we will use for our elliptic curve, y2 minus y1 into x2 minus x1 inverse if p not equal to q, if p not equal to q, and it is basically 3x1 square plus a 2y1 inverse if p is equal to q. So, this is the formula for addition. So, now this under this addition you will form a group. So, we will use that group to have a ElGamal cryptosystem. So, we will take an example. So, suppose our p is 11 and we take a curve under Z11. Sorry. So, suppose we take this curve y square equal to this, you have seen in the last class, x plus 6, and this is over Z11. So, our points are coming from Z11, or p is 11, and we have seen the points are basically so E is basically we have seen these points like 2, 4, 2, 7. Let me just write it again. 3, 5, 3, 6. So 5, 2, 5, 9, and then excuse me, 7, 2, 7, 9, and we have 8, 3, 8, 8, and 10, 2 and 10, 9. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, this along with the pointer infinity. So, this will form a group over elliptic curve point. These are the elliptic curve points, and this will form a group over ZP. Now, we need to choose a primitive element. So, this is a finite group and 13 elements. So, we need to choose a primitive element. So, let us try to get a primitive element, so that we can construct a the ElGamal cryptosystem. Let us choose alpha is say 2, 7, and we can just verify whether this is a generator of that group or not. So, how to verify this? So, if we take this, now how to calculate 2 alpha? 2 alpha is basically plus 2, 7. Okay. So, now this is the addition. This addition formula is written over here. So, this is the case when p is equal to q, p is equal to q. So, we have to use this formula x3 is, so everything under mod p, this is also under mod p, this is also under mod p. So, we just simply use this formula x3, we calculate lambda square. So, lambda square will be coming from this formula when p is equal to q. So, this is under mod p. So, we just calculate this value and we got lambda, and so lambda is basically coming from this formula 3 into x square, x1 square is 2 square plus 1 into, so a is 1, this is the curve, 2 y1, so y is basically 7, so 2 into 7 inverse mod 11. So, this is basically coming out to be 2 into 3 inverse mod 11. So, this is basically 2 into 4 mod 11, this is 8. So, lambda is coming out to be 8. So, once we have the lambda, once we have a lambda, so we can use this formula to get this x3 and y3. So, sum. So, basically then x3 will be, so lambda square 8 square minus y1 minus y2. Here y1 y2 is same, which is basically 2 minus 2 mod 11. So, it is giving us basically 5, and y3 is basically, so y3 is basically this formula. So, 8 into 8 into 2 minus 5 minus y1. So, minus 7 mod 11. So, this is coming out to be 2. So, that means 2 alpha is basically 5 comma 2. So, we got this 5 comma 2. So, similarly, we have to calculate 3 alpha. So, this is in additive sense. So, this operation is additive sense operation. So, it is instead of power, it has this 2 alpha 3 alpha. So, 2 alpha means alpha times alpha, alpha we operate, and 3 alpha means alpha operate alpha operate alpha. So, like this is in additive sense. So, how to calculate 3 alpha? So, we got 2 alpha, then to calculate 3 alpha. So, 3 alpha is basically 2 alpha plus alpha. Now, 2 alpha we know, just now we have calculated, and alpha is this. Now, for this also we have to use the formula, but here p q are not same. So, we have to find this addition p plus q. So, this is x1 y1 x2 y2. So, p q are not same. So, if p q are not same, this is the lambda. So, if we use the same formula, we will be getting this as a say 8 comma 3, 8 comma 3, this one. So, similar way, if we continue, so 4 alpha will be 10 comma 2, 5 alpha will be 3 comma 6, 6 alpha will be 7 comma 9, and 7 alpha is 7 comma 2, 8 alpha is basically, so this we have to calculate. So, 3 comma 5. So, we have to calculate based on this addition rule. 3 comma 5, 9 alpha is basically 10 comma 9, and then 10 alpha is basically 8 comma 8, and 11 alpha is basically 5 comma 9. Like this we continue, 12 alpha is basically 2 comma 4. So, if we just check, we are getting all the points. So, alpha is basically a primitive element. So, alpha is equal to 2 comma 7 is a generator of this group, is a primitive element. So, we got the primitive element. So, we can use this to have a ElGamal cryptosystem. Okay. So, how we can do that? So, basically, so this setup is done by Bob. So, Alice wants to send a message to Bob, and they are going to use these elliptic curve points. So, Alice wants to send a message to Bob, and they have decided to go for ElGamal cryptosystem over the elliptic curve points. Okay. So, and discrete log problem is quite hard here, because to calculate itself this addition is expensive. So, we have to calculate lambda, we have to calculate this x3 y3 like this. So, the discrete log problem over this elliptic curve point is hard. So, if we assume that, then we have a ElGamal cryptosystem over this. So, the Bob chosen this alpha, this is the setup phase. So, this is the elliptic curve. So, the primitive element is 2 comma 5, this is Bob, and then Bob choose a which is 7 say, and then Bob calculate beta. So, this is 7 alpha, which is basically 7 alpha is basically 7 comma 2, 7 comma 2. Okay. So, now the encryption. So, then Bob make this public, this is public, this is public, and the elliptic curve points are public. Only secret is this k. Now, suppose Alice wants to send a message x, which is coming from the elliptic curve point E. So, this is Alice wants to encrypt. So, Alice has to choose also a k, which is the random number. So, Alice will encrypt using this Bob public key. So, Bob public key is basically EB is basically alpha, beta, and obviously the elliptic curve. So, encryption of x comma k using EB is basically y1 y2, where y1 is basically, so y1 is basically what? Y1 is basically k times alpha, and y2 is basically x plus. So, this is masking. So, our operation is addition operation. This is plus k times 7 comma 2. This is the beta. So, beta to the power k. So, this is the additive sense. So, k plus beta. So, this is basically, and so this is basically encryption, and the decryption is, so the decryption is, decryption means Bob is receiving y1 and y2. So, Bob will just calculate, apply this using this Bob secret key db on this y1 and y2 is basically y2 minus 7 y1. So, this is in additive sense. So, basically it is y1 to the power 7. So, additive sense 7 y1, then inverse is basically minus. So, Bob will calculate this. Now, suppose let us take an example. Suppose x is, the message is say 10 comma 9. So, Alice choose this message to send, and Alice choose k is equal to say 3. So, then Alice will calculate this y1. Y1 is basically 3 into this. So, this is basically 8 comma 3. So, 3 alpha, 8 comma 3, and x plus this. So, this is basically x is 10 comma 9 plus k is 3 and 7 comma 2. So, this if we calculate, this is 10 comma 9 and this will be 3 comma 5 and this is basically 10 comma 2. So, this is y1 and y2. So, this y1 y2 is send it to Bob, and upon receiving this y1 y2, how Bob will get back. So, Bob is receiving this 8 comma 3 and 10 comma 2. This is y, this is the ciphertext y1 y2. So, what Bob will do? Bob will simply do this y2 minus 7 8 comma 3. So, this will be basically 10 comma 2 minus 3 comma 5. So, minus 3 comma 5 is basically plus 3 comma 6. So, this is basically 10 comma 9, which is the message sent by Alice. So, this is the ElGamal version over the elliptic curve points. So, if we can have a group, typically if it is a cyclic group, then it has a generator, and then we can construct a ElGamal version over that group. So, this is over the elliptic curve points. Thank you.